Hello everyone, my name is Atul. I will be talking about single-photon 3D cameras. There are many real-world applications where we need to capture images in photon-starved scenarios. A conventional camera cannot reliably operate in such low illumination conditions. If it doesn't get enough light, it cannot make an image, let alone recover 3D shape. Fortunately, there is an emerging class of extremely sensitive sensors called single-photon sensors that can capture individual photons. Furthermore, they can record the time of arrival of each photon with very high time resolution. This makes them a natural candidate for 3D imaging using the time-of-flight principle. Recall that a 3D time-of-flight camera computes depth of the scene using the speed of light and the round-trip time of a laser pulse. Many commercially available 3D imaging devices use this time-of-flight principle for a wide range of applications. Now let's see if we can use a single-photon sensor with these cameras. Let's look at the single-photon image formation model first in a simple scenario. The scene is illuminated only by a laser source that periodically emits a light pulse. The sensor then receives time-shifted pulses in the form of photon streams. For each stream, it detects only the first photon. This is the defining property of single-photon sensors, and we'll keep using this. Using only the first photon of each pulse, the sensor makes a timing histogram. Because there is no ambient light, the shape of this histogram resembles the shape of the shifted pulse, and we can easily estimate the time of flight. Note that it only takes a few microseconds to acquire these measurements for one histogram. So a single photon sensor can recover 3D shape quite accurately in the dark. But in order to be practically useful, these sensors need to adapt to a wide range of illumination levels, both extremely dark and extremely bright, as well as high dynamic range. So let's look at the case where there is ambient light, for example sunlight in the scene. The incident waveform now has a vertical shift due to sunlight, and many ambient photons appear in each cycle. But this causes a problem. The first photon in every cycle is likely going to be an ambient light photon. This distorts the captured histogram, and the true peak gets buried under the ambient photons. This makes the peak hard to locate. Note that this problem cannot be overcome by increasing the source power. Later arriving source photons will still be masked by early arriving ambient photons. We propose a new asynchronous mode of operation that avoids the problem of sunlight distortion. Observe that the probability of detection decays exponentially starting from the time when the sensor is turned on. Conventionally, the sensor is turned on immediately after the laser pulse is transmitted. Therefore, the probability of photon detection at the true peak is very low. In asynchronous operation, we shift the start of the sensor with respect to the laser. This increases the probability of capturing the source photons that arrive later in the cycle. We then align the sensor cycles to the laser period, which makes the peaks line up. By summing these measurements over many cycles, we get a histogram like this. As we increase the number of shifts, the histogram starts resembling the true waveform shape, free from sunlight distortion. This is the key idea of asynchronous acquisition. Asynchronous acquisition enables depth estimation even under high ambient light, unlike conventional acquisition where the peak is buried in noise. One way to achieve delayed start times is to make the sensor cycle longer than the laser cycle. However, this is not very time efficient. A better way to achieve asynchrony in practice is to let the photons themselves determine the cycle lengths. We call this photon-driven acquisition. Due to randomness of photon arrival times, we automatically achieve staggered start times. We now show some experimental results. The first experiment shows a scene with large dynamic range of reflectivities. The bright vase has almost an order of magnitude higher reflectivity than the black vase. Photon-driven acquisition can automatically adapt to a wide range of reflectivities and recover an accurate depth map. In our second experiment, we imaged a white porcelain flower vase under bright ambient light. Photon-driven acquisition provides almost an order of magnitude improvement in depth accuracy. In conclusion, single-photon cameras can be an attractive candidate for real-world imaging applications that witness a wide range of illumination conditions. Our work takes some initial steps towards using these cameras for extreme vision applications. Thank you for watching.